In one of the most remarkable discoveries of the 20th century, scientists found that the universe is not a static and unchanging entity. Instead, space itself expands over time. This means that distant objects within the universe are moving farther apart as the very fabric of the cosmos stretches. This phenomenon is observable in every direction, demonstrating the dynamic nature of the universe. Even 100 years after this revelation, it remains a fascinating and mysterious concept, particularly for astronomers and cosmologists. Naturally, questions arise. If the universe is expanding, what happens to the fabric of space itself? Is space stretching and thinning? Is new space being created as expansion occurs? If the universe has been expanding all this time, what is it expanding into? And are we, as part of the universe, expanding as well? These questions challenge our imagination and remain some of the most intriguing topics in modern astronomy. Fortunately, recent data from the James Webb Space Telescope is providing new insights to help illuminate these mysteries. To delve deeper, we need to start with the framework of general relativity, Einstein's groundbreaking theory of gravity. At its core, general relativity connects two seemingly unrelated concepts: the distribution of energy, including matter, antimatter, dark matter, radiation, and more, and the geometry of spacetime itself, including how it bends, warps, and evolves. For example, in a universe devoid of matter and energy, spacetime would remain flat and static, similar to how we intuitively perceive Newtonian space. However, introducing even a single mass into this empty universe would warp spacetime around it. This warping would affect the motion of objects, compelling them to move toward the mass. If the mass were spinning, spacetime would twist more intricately, following rules like those of the Kerr metric. In these scenarios, spacetime is still static in the sense that distances and structures within it do not change over time. Whether we observe such a spacetime now or a billion years later, it remains fundamentally the same. In such cases, there is no cosmic expansion or contraction. However, the situation changes dramatically when we consider a universe filled evenly with matter and energy. Observations show that our universe is both isotropic, appearing the same in all directions, and homogeneous, having a uniform distribution of density and temperature on large scales. These properties are confirmed with remarkable precision, exceeding 99.99%. Under these conditions, general relativity dictates that the universe must either expand or contract. This insight was formalized by Alexander Friedmann in 1922, who described equations governing the evolution of such a universe. These equations make it clear that a universe uniformly filled with energy cannot remain static. It must evolve. But what does this expansion mean for the fabric of space itself? Space is not something we can directly measure or manipulate. It's not like a physical object that can be handled in a lab. Instead, we observe how space influences measurable phenomena, such as the behavior of matter, light, and energy, and use this information to infer its properties. For instance, when examining black holes, we observe how spacetime is warped by their immense gravity. This warping affects nearby objects and light, and these effects align perfectly with predictions from general relativity. Similarly, if a black hole rotates, it drags spacetime along with it, creating complex distortions. By studying these distortions, scientists confirm the validity of Einstein's theory in a wide variety of situations. To date, every observation has supported general relativity, even in extreme environments. Gravitational redshift, the stretching of light as it escapes a strong gravitational field, has been observed in stars orbiting black holes, light traveling through Earth's gravity, and even light passing through massive galaxy clusters. These phenomena, along with others such as gravitational time dilation, light bending, and the behavior of celestial objects, consistently match Einstein's predictions. Despite over a century of scrutiny, general relativity remains an unshaken cornerstone of modern physics. As we continue to gather data, including groundbreaking insights from the James Webb Space Telescope, our understanding of the universe's expansion, and the very nature of spacetime itself, will only deepen. Einstein's theories offer profound insights, but what can we say about the universe's expansion? When we consider the expanding universe scientifically, The key question we must ask is this: are we equipped to adjust our understanding of measurements within the cosmos? Fundamentally, we can only interpret what is observable. Beyond that, we risk projecting our limitations onto reality, placing a veil over what we comprehend. In modern cosmology, the expanding universe presents a simple yet profound concept: density. Assuming the universe is filled with matter, as space expands, the volume containing this matter also increases. Matter, in its simplest form, refers to the physical stuff that occupies space. As the universe grows, the total amount of matter remains constant, but the space it inhabits grows larger. Density, defined as mass divided by volume, decreases as a result. Calculations in general relativity align with this observation. While the universe contains various forms of matter, such as ordinary matter, black holes, dark matter, and neutrinos, not everything in the cosmos is matter. Radiation, for instance, exists as quantized particles of energy. As the universe expands, the wavelength of light stretches, shifting towards the red end of the spectrum, a phenomenon known as redshift. This effect was the first indication of the universe's expansion and is observed in quasars and distant galaxies. In addition to matter and radiation, the universe also contains dark energy. Unlike particles, dark energy appears to be an intrinsic property of space itself. Although it cannot be directly measured like the frequency of photons, its effects are inferred by observing the relationship between redshift and distance in celestial objects. These observations reveal that dark energy constitutes approximately 2/3 of the universe's total energy today. Interestingly, the energy density of dark energy remains constant as the universe expands, distinguishing it from other forms of energy. By piecing together data from various sources, a coherent picture of the universe emerges. Presently, the universe expands at a rate of approximately 70 kilometers per second per megaparsec, 3.26 million light-years. This means that for every megaparsec of separation between two objects, the expanding universe induces a redshift equivalent to a recessional velocity of 70 kilometers per second. Studying redshifts across greater distances and over time provides insight into the universe's past expansion rates, enabling us to understand its composition at different stages. Today, the universe is composed of the following energy components: radiation, about 0.8% in the form of photons, electromagnetic radiation; neutrinos, roughly 0.1%, which now behave like matter but acted as radiation in the early universe; ordinary matter, approximately 4.9%, including atoms, plasmas, black holes, and other forms derived from protons, neutrons, and electrons; dark matter, around 27%, whose exact nature remains unknown, but it behaves like massive, gravitationally interacting matter; dark energy, about 68%, acting as an intrinsic energy property of space itself. By extrapolating backward from these current observations, we can determine the dominant forms of energy at different stages of cosmic history. Measuring the present expansion rate and its evolution over time allows us to not only understand the universe's current state but also glimpse its past and foresee its future. The future of our understanding of the universe depends on refining our perceptions to shape a definitive understanding of cosmic evolution. The James Webb Space Telescope has deepened the ongoing crisis in cosmology. Observations of stars and galaxies by both James Webb and Hubble reveal that the universe is expanding faster than expected based on current models. Evidence of this discrepancy has been accumulating for years, leading some scientists to describe it as an impending crisis in cosmology. Nobel Laureate Adam Rees, who led a recent effort to probe this inconsistency, remarked that the universe often surprises us, which is beneficial for scientific learning. If the observed Hubble tension indeed reflects physical reality, resolving it might require adding new elements to the universe's fundamental components. One prominent theoretical candidate, early dark energy, suggests that around 50,000 years after the Big Bang, there was a brief burst of dark energy. This short-lived phenomenon could have altered the early universe's development enough to resolve the Hubble tension without disrupting much of the standard cosmological model. However, This adjustment would lower the universe's estimated age from 13.8 billion years to about 13 billion years. Astrophysicist Mike Boylan-Culchin from the University of Texas at Austin pointed out that introducing such a fleeting phenomenon feels counterintuitive, but the inconsistency in observation suggests that exploring unconventional ideas might be necessary. In a study published in the journal Classical and Quantum Gravity, Dr. P.K. Sesh and his colleague B. Anup from the University of Hyderabad proposed a solution to reconcile the conflicting results. They argued that current models rely indirectly on Einstein's theory of general relativity, which might need revisiting to account for quantum effects. These effects include random field fluctuations and spontaneous particle creation from the vacuum of space. While incorporating quantum effects into various fields has been successful, applying them to gravity remains a significant challenge due to the difficulty of making precise calculations. Dr. Sesh and Dr. Anup focused on broader quantum gravity effects common to many theoretical frameworks. Their analysis suggested that incorporating quantum effects into the gravitational interactions during the universe's earliest phase, known as inflation, could potentially align the Hubble tension measurements. While definitive conclusions await a comprehensive theory of quantum gravity, these initial findings are promising. Moreover, the connection between the cosmic microwave background and quantum gravitational effects paves the way for future experimental studies of these phenomena. The expanding universe and its boundless nature. The question of what the universe is expanding into is rooted in our observations of its growth. Our observable universe, limited by the speed of light, the expansion rate, and the time elapsed since the Big Bang, is likely just a small part of a much larger, possibly infinite cosmos. Over time, light from distant regions will expand our observable universe, doubling its current apparent volume. However, the unobservable universe may be infinite, rendering questions about what it expands into meaningless, an infinity beyond infinity. The concept of inflation suggests that our universe is just one region among many within a vast multiverse, where countless Big Bang events may have occurred. Yet, our universe does not expand into this multiverse. Rather, it contains all that exists, with no external boundary to expand into. Instead, cosmic expansion is an intrinsic property of space itself. Within gravitationally bound systems like galaxy clusters, e.g., the Virgo cluster, the effects of expansion are overridden by gravitational forces. Locally bound systems, atoms, people, stars, and even large galaxy groups, are not subject to this universal expansion. Beyond the largest gravitationally bound structures, typically 1 to 2 billion light-years across, cosmic expansion becomes significant. This understanding clarifies that while space itself expands, it does not do so into anything else. Instead, the universe expands into itself, governed by its inherent spatial properties. This self-contained expansion reflects the profound and fascinating nature of the cosmos.